Okay, so my name is Jee-Woo Park, and before I go on, I first want to thank the organizers, Shamik and all the organizers for inviting me to give these lectures. I work on cold atoms, especially with Bose-Einstein condensates, and it's my first time visiting India. It's kind of my homage to Bose, so it's really a great honor. In light of the winter school, I've changed my title to be a long-range interactions in quantum gases and tweezer arrays. So I think I have about 3 lectures, Monday, Tuesday, and Thursday. Today I'll be covering some basic cold atom things.
Close to the center, so
sure.
You are visible in the camera.
Oh, should I be here?
Like this part.
Because I think I'll be.
This part is fine.
So okay, I'll be here. All right. So today I'll talk about atomic gas experiments. Tuesday about polar molecule experiments, and then on Thursday a little bit about molecules, and then about tweezers, optical tweezer experiments. But before I go on, I want to do a brief head count of are there experimentalists in the audience? I know there's one. I'm an experimentalist. Okay, so at least a couple. So I'm not alone. So it makes me a little bit less easy to give my talk in front of almost a pure group of theorists, but hopefully I can entertain you guys. And if you have challenging theory questions, those can be directed to the theory lecturers in the audience, and I'll be happy to discuss anything related to the experiments to the best of my knowledge. Okay, so I told you that I'm from POSTECH, and POSTECH, I'm not so sure if any of you would have heard about this institution. So this is a research institution based in South Korea. So I flew in from Korea last night. And so this is roughly where we are in Mumbai. And if you zoom in, this is roughly where I do my research in the southern eastern coast of the Korean peninsula in a city called Pohang. And Pohang is well known, I think, if it is well known, it's known for its steel manufacturing industry. So we have a very large steel manufacturing company. I think it's the second largest in the world. And then it's the host to the Marine Corps of Korea. So we have our boot camp in Pohang. And also, it's by the Pacific Ocean, so a lot of people come visit Pohang to do exotic sports like surfing, kite surfing, and whatnot. So, but in any case, Pohang is known for one additional factor, which is it's home to my institution, which is the Pohang University of Science and Technology. We are actually a very small school. We have about 350 incoming freshmen every year, so on the order of a few thousand undergraduates and graduate students. So it's a very small-sized institution in Korea that's actually modeled after Caltech in the US. So in terms of the visibility, so within the group of small universities, we have a fairly strong research program that we maintain. Especially within the physics department, we specialize in condensed matter experiments and optics. So if you've done optics experiments, you might have heard about the Hong-Mandel experiment, which is a typical way of how you measure correlations in single photons. And Professor Hong, to many people's surprise, is actually a Korean, and he started his career at POSTECH, and he's now an emeritus at our institution. So we have strong sectors in condensed matter and optics. And the reason why we have such a strong condensed matter sector is because we are home to a research facility, a national research facility, which is the linear E-beam accelerator that's producing X-ray radiation, coherent X-ray radiation that people use for spectroscopy experiments. So a lot of foreigners come visit our institution to do experiments on their samples using our X-ray radiation. And secondly, we are also host to the Asian Pacific Center for Theoretical Physics, which you may have heard about. So it's it's a large APEC institution that's really serving as a hub for scientific collaboration, especially theoretical physics collaboration within countries in Asia. And I know that India is also one of the member countries of APEC, and we run a lot of research programs for young research scientists, fellow positions, and postdocs. So if you ever, also a lot of summer and winter schools, so if you ever happen to visit Pohang for any of these reasons, please just shoot me an email. I'd be happy to arrange lab tours and discussions for you. And I really hope you will also have an opportunity to visit my institution in some future. So with that, so my group, we started in the year 2020 when the COVID pandemic was at its highest, and I'm an experimentalist, so constructing a new experiment at the peak of COVID was not a simple task. But in any case, we have kind of a two-track experimental approach. So one experimental system deals with constructing a quantum gas microscope of polar and AK molecules. I'll talk a little bit more about what that means. And a second experiment that we just started to construct as of last winter is trying to assemble polar molecules that experience strong dipole-dipole interactions in optical tweezers so that we can construct a filled tweezer array of potassium cesium molecules in the experiment, which hopefully will be useful for quantum information processing, but also for exploring many interesting many-body physics in the presence of long-range dipole-dipole interactions. So the outline of my lecture, so today I'll give you I already gave some introduction. I'll give some more introduction into our research field of cold atoms and go on to talk about cold gas experiments, and especially focus on, or at least today focus on dipolar atomic gases, which is one of the many ways or few ways of engineering long-range interaction in these cold gas experiments. And then tomorrow's lecture and part of Thursday's lecture will focus on polar molecules, which is another way to engineer long-range interactions, but much stronger long-range interaction than using magnetic atoms, dipolar atoms. And then if there is more time, then I'll talk a little bit more about optical tweezer experiments, Rydberg atoms and tweezers, and also polar molecules and tweezers in the remaining time. So hopefully I'll be entertaining. Okay, so these days I think we really live in this heightened sense of quantum computing, quantum technologies and whatnot, but personally as a physicist, my view on this thing, or the interest in this development, is because for physics, I'm hoping that these developments within quantum technology can actually help me better understand challenging issues of quantum many-body physics. And of course, you guys are all theorists, so I can almost skip this slide. But just want to say that usually when we think about strongly correlated systems, we tend to immediately jump to thinking about condensed matter systems like ITC, quantum magnetism, and topological systems. But I just want to say that even a very simple system of a diatomic molecule consisting of two ions and a bunch of electrons, could be considered a many-body. It's a few-body system, but not only understanding the inner workings of, let's say, high-temperature superconductors consisting of 10 to the 23 electrons and whatnot, is extremely challenging, but also turns out understanding the inner workings of a simple diatomic molecules and the level structure of these molecules is actually an equally interesting and challenging task. And so a typical program or a theoretical approach that allows us to calculate the internal structure of a simple atom like an alkali atom, when you extend that approach to constructing the internal states of a diatomic molecule, we know that it fails dramatically because of the non-trivial correlations in the electrons in these few-body systems. And interestingly enough, one of the things that these companies like Google and IBM with their kind of NISQ era quantum computing systems, that one of the pressing topics that they pursue is trying to use their simple hardwares, well, not simple, but their quantum computers to try to come up with algorithms that can calculate the energy structure of these simple diatomic and triatomic molecules, which was actually featured as a cover of Nature a few years ago. Of course, as someone working on cold molecules, I see this line of development very interesting, because I personally work with these molecules in the quantum regime where I can isolate single quantum states of these molecules and actually control them. So in any case, so why are these correlated systems hard to understand? Of course, the reason is abundant, but the key reason is because in quantum mechanics we have superposition and entanglement. So already Darius mentioned in his lecture, so if we already think about a fairly simple system of just interacting spins of n spins, classically if we wanted to specify the classical state of an interacting n spin system, I just give the state of the relative of all of the spins, whether they're pointing upwards or downwards. So that would be like a n classical bit representation of a classical system. But of course, in quantum mechanics, you need to consider all the possible combinations of all the spin orientations. That means that we have now an exponentially scaling Hilbert space. And that's just to keep track of the quantum state itself. If you wanted to do any meaningful time evolution, you'd need an exponent times exponent dimensional operator that you have in your computer system to classically simulate the dynamics of this spin system. And of course, this exponential scaling comes to bite you fairly quickly, because already for just 50 of such spins, which seemingly looks like a small quantum system to consider, but because of this exponential scaling, it turns out that the number of classical bits that you would need to represent a 50 quantum spin system is on the order of 2 to the 50 classical bits. But as it turns out, some of the most powerful classical computers that you can have access to, for instance, this Titan supercomputer at Oak Ridge National Labs. I think the Titan used to be the most powerful supercomputer maybe like 10 years ago. I think it's now like the third or the fifth, but already still impressive. But the amount of cache memory that you have in these supercomputers is on the order of 2 to the 50 bits. So already in the current status of things, dealing with about 50 quantum spins in a very exact manner is already at the limit of what classical technology can take. And of course, this feels like we're hitting a very hard wall. But whenever we see a very big challenge, we try to step on the shoulders of our predecessors. In this case, would be Richard Feynman, who said that you can kind of try to flip the coin around and think in an opposite sense. So if you imagine having a fully controllable quantum systems, then maybe you can actually make use of this complex computational power as a resource. So this is really kind of the seeding idea or the notion of quantum simulation, which now extends to quantum computing. And so building upon this vision of a quantum processor where we can individually control the quantum states of all the particles that we have in our many-body system, not only the individual quantum states, but also the interactions between pairs of particles in our many-body system. And using these quantum processors in modern day, they're kind of two kind of similar but different routes, where one is in the direction of analog quantum simulation, and the second is in the direction of digital quantum computation. So analog quantum simulation, I can take this analogy from classical physics. So if you lived in the era of Newton, for instance, and you are interested in understanding the motion of stars and planets, you would make a device that would look something like this, with gears and fake planets, and you would kind of spin your gears around to kind of simulate what the orbital motion of all of these planets would actually look like. If you put that into the quantum regime, analog quantum simulation works on a similar principle. So with our highly controllable quantum systems, we try to make our system actually implement a meaningful problem almost as exactly as possible. So for instance, if we're interested in understanding high temperature superconductivity, we have this Hubbard model that we would love to understand better. And then in an approach of analog quantum simulation, what we would do is we would try to trap atoms in an optical lattice where these atoms can hop around in the lattice site, implementing the tunneling term. And then as they tunnel around, when two atoms happen to sit on top of each other, it implements the on-site interaction term U. So we try to really emulate, given an interesting or important Hamiltonian, try to emulate verbatim what this Hamiltonian looks like on a physical controllable quantum system. So that's in the direction of quantum simulation. Quantum computation kind of works in a similar fashion as classical computation. So so if the program of analog quantum simulation is kind of goal-oriented or problem-oriented, the approach of digital quantum computation is more hardware-oriented. So we have a fixed set of building blocks of a quantum computer, say qubits and gate operations. And using these gate operations, what's then remaining is for us to think about meaningful algorithms that we can make of or implement using this well-defined set of building blocks of our quantum computing system. For instance, like a Shor algorithm for factorization. So in any case, regardless of whether you pursue the analog direction or the digital computation direction, there are some hardware criteria that we need to satisfy if we think about implementing physical systems. And the key requirements for both approaches is that we need to have full quantum control, full coherent quantum control of the single particle states of the building blocks or the building particles of our many-body system. And secondly, we need to be able to have control of interactions. So in a quantum computing language, this would translate to us having highly efficient two-qubit gate operations. The first would correspond to having highly efficient single-qubit gate operations. And of course, the system should be scalable because we want to be able to deal with meaningful problems that's hard to deal with in the classical sense. And so currently, kind of in the market for quantum platforms, there are a number of different experimental approaches to engineering quantum controllable systems, one of which is ultra-cold atoms, which is a platform that I love the most and I work with. Another platform is trapped ions. They're very similar, but somewhat different in the way these experimental platforms work. Another is superconducting circuits that you all heard about and read about in the news. And in addition, you have NV centers, quantum dots, also photons as a source of controllable quantum system, which I think you'll hear more about next week in next week's series of lecture. So I work with neutral atoms. So when I say neutral atoms, what kind of sample, physical sample or physical ensemble should you think about? So typically in cold gas experiments, we work with atoms that are kind of easy to deal with using lasers. The simplest would be something that looks like a hydrogen atom, so that would be alkali atoms. So for concreteness, you can imagine having a gas of alkali atoms like sodium, lithium, or potassium, or rubidium. And in our very clean vacuum chamber, which I'll explain in a bit more in a few more slides, we have these atoms, about 10 to the 4 to 10 to the 6 of these atoms trapped inside a vacuum chamber. And these atoms are cooled to a temperature scale of typically of about 100 nanokelvin. So if you, and the typical spatial dimension of these clouds that we work with are on the order of about 100 microns. So if you put these dimensions and do a calculation, you'll immediately see that these gases are extremely dilute. So we have about 10 to the 10 to, and a condensate about 10 to the 15 particles per cubic centimeter, whereas I think that's like at least 7, 8, or even more orders of magnitude more dilute than what we experience right now in air. So the interparticle spacing between these particles is fairly large, on the order of micron. But then the key thing is that the temperature is actually so cold that even with these large interparticle spacings, the system as a whole still behaves quantum mechanically. I'll get to this in a little bit more. So compared to typical strongly correlated systems that you will consider in condensed matter experiments, these cold gas experiments, the dynamics is much slower. So the kind of physics that would happen in a kind of a conventional condensed matter system on a time scale of picosecond would happen in our experiments on the time scale of milliseconds, which is much more favorable for experimentalists to actually see this kind of dynamics. So that's kind of one of the powers of working with these cold atom experiments. So the typical many-body energy, if you were trapping fermions, would be on the order of 20 kilohertz, so 0.1 nanoelectron volt. So that's really low compared to a typical solid-state system. And with these cold gases in our hand, the key thing as a quantum simulator or a quantum computer or a quantum computing platform is that we can control the behavior of these individual particles extremely well. So the list of things that we can actually control in the experiments, first of all, we have a handle on quantum statistics. So if you look at the periodic table, yeah.
So how are these very low temperatures attained? These are very low temperatures. How do you go to this low temperature?
Yeah, I'll get to that into these in a few more slides. Yeah. Okay. So one handle that we have is quantum statistics. So if you look at alkali atoms or laser coolable atoms, some of the atoms actually have isotopes, which are bosons and fermions. So you can actually choose to cool bosonic atoms into these low temperatures, or choose to work with fermions and cool them to very low temperatures. So you can change the quantum statistics of your many-body system. Second thing is you can control the dimensionality of your system. So the picture that I just showed you, it's a bulk gas in 3D in a harmonic trap. But of course, using a technique known as optical lattices or engineered optical traps, you can prepare these gases not only in 3D, but also in 2D, in a single layer 2D, or stacked layers of 2D systems, or even in 1D tubes. And if you put this control of dimensionality to the extreme, you can actually engineer a lattice experiment with full lattice structure and really try to access Hubbard physics. The third thing that we have control over is the impurity. So if you have type A of atoms cooled down to nanokelvin temperatures, and imagine mixing in a little bit of type B atoms into your system, then from the perspective of type A atoms, the B atoms look like impurities, where you have very precise control over the doping of your impurity atom. So you can work with mixtures. Also, you can use randomly positioned laser beams that atoms feel as potentials, and you can use that as a quasi-random optical impurity to access physics related to Anderson localization and in the presence of interactions, many-body localization. And perhaps the most important thing that we can control in our experiments is the interaction between a pair of atoms using a technique known as Feshbach resonances, which I'll talk about on tomorrow's class. So if you have a pair of atoms, there's a way in which we can control the scattering length of the collision between these pairs of atoms at will. So we can make these pairs of atoms weakly interact, weakly repel, but also weakly attract. Or we can tune a magnetic field that we apply to these atoms and make these atoms collide as strongly as quantum mechanics allows them to be in the unitary regime. So we have full continuous control over the interaction strength in these atomic gas experiments, which is one of the key reasons why these experiments are such a good many-body model simulator. And this has been put to full use in these experiments that look at the Bose and Fermi-Hubbard models, especially using a microscope objective that allows you to image individual single atoms in these optical lattices. So this is an image from Marcus Greiner's group at Harvard looking at the Fermi-Hubbard model, where you see the antiferromagnetic patterning of these gases at low temperatures below the Néel temperature. And also, second key application is also in the direction of studying fermionic superfluidity. So using this Feshbach resonance in a spin mixture of fermionic atoms in these experiments, we can really do a very careful study of the BEC-BCS crossover mechanism of fermionic pairing in spin 1/2 systems, which, for instance, a lot of key work has been done in Martin Zuberlein's group at MIT. So not just lattice systems, but bulk gas experiments are still very interesting quantum simulators because, as it turns out, the crust of the neutron stars or the quark gluon plasma that was created in the early universe, people believe were actually fermionic superfluids. So an analog quantum simulation of such physical systems would be a spin 1/2 mixture of fermionic atoms that are condensed to become a superfluid in the BEC-BCS crossover. And the study of vortex nucleation, for instance, would help us understand kind of the dynamics of, or the vortex dynamics that arise in these neutron stars that give that give rise to the birth and death of these stars as to the far as I know. So with these experiments, the typical images we can take, you can engineer, you can use laser beams to really take movies of vortex dynamics in these cold gas experiments and really try to simulate these results using a supercomputer that I just showed you, the Titan. These are fermionic particles, so a numerical simulation is extremely challenging, which is the reason why they use a supercomputer in the first place. So these are very interesting experiments in their own weight. But I promised you I'd talk about long-range interaction in these atomic gas systems. So these neutral atom experiments, especially working with ground state alkali atoms or alkaline earth atoms, are great. So I've already shown you a number of exciting experimental results that people have been studying in the past 20, 30 years. But from the perspective of studying many body systems, there's one shortcoming, which is that the underlying interaction between a pair of neutral atoms, I'll talk about this a little bit more in the coming slides, are assumed to be simple contact interactions. So we model the interaction between a pair of neutral atoms as a delta function.
So when you talk about the phase resonance between two pole atom particles,
Pardon?
resonance between the two pole atom particles, then the resonant particles decays to something else, and
You're asking if we can have
phase back resonance that you mentioned.
phase diagram of which Hamilton?
Phase back resonance.
Feshbach resonance. Yeah, near Feshbach. Okay, I'll talk about this on tomorrow's lecture. Yeah, the reason why we have Feshbach resonance is because there's a nearby molecular state. And yes, if you work near a Feshbach resonance, these pairs of atoms can decay into the molecular state, which can immediately leave our trap. But with fermions, you're kind of saved by Pauli exclusion because the way in which losses occur near a Feshbach resonance is that a pair of atoms will become a molecule, but you need to conserve energy and momentum together. So you need a third particle that will take out the excess momentum. So your loss mechanism is a three-body loss. But because of Pauli blocking, if you have a spin 1/2 system and you have strong interaction between spin up and spin down particle, the third particle will either be spin up or spin down, which will be Pauli blocked either way. So that kind of saves you. And that's one of the key reasons why you can actually condense fermionic spin 1/2 atoms into superfluids. Yeah. Okay, so that was kind of going further out, but please feel free to ask. And from anybody's perspective, interesting interactions or interesting physical phenomena in nature are often based on long-range interactions, like Coulomb interactions or gravity. And these interactions can also are also oftentimes anisotropic, like in the interaction between magnets and spins. So naturally, within our community of cold gases, there's been kind of a long push for us to figure out new, highly scalable, controllable cold gas experiments or cold gas platforms where we can induce strong long-range anisotropic interactions, namely dipole-dipole interactions. And so in that regard, especially focusing on these gaseous systems, there are a number of options that we have in our hand. The first option, extending our experiments with neutral atoms, is to promote these atoms into a highly electron-excited state, which are called Rydberg states. And in the Rydberg state, because of the electron cloud is so large relative to the core, these Rydberg atoms are extremely highly polarizable, which gives rise to long range, well, it's not long range, it's long distance. I'll get to this in a bit, but which gives rise to long distance interaction. Of course, with Rydberg atoms, in typical these teaser experiments or in typical Rydberg atom experiments, the underlying interaction between a pair of Rydberg atoms is still 1 over R6, but the characteristic distance of the interaction is very large, to the point that it's comparable to the distance between a typical pair of Rydberg atoms. So in that sense, it's long distance. It might not be long range in the pure many body sense of the terminology, but if you're careful to engineer which Rydberg states you use, it's still possible to engineer 1 over R to the cube interactions in these gases, and a lot of recent experiments with tweezers, newly built experiments with tweezer arrays are pushing towards this direction to engineer 1 over R cubed interactions. The key advantage of working with Rydberg atoms is that the electric dipole moment is extremely large. It's on the order of 100 dBi. You might not have I personally didn't have a good sense of what dipole, kind of how large a unit of a dBi is. And I'm sure it's the same for many of you guys. But if you think about a very dipolar molecule in nature that we often discuss, it's a water molecule, right? A water molecule has a dipole moment of about 1.8 dBi. So these Rydberg excited molecules, atoms, are extremely dipolar, so to speak. So they experience extremely strong, potentially dipole-dipole interactions. You can engineer them to experience very strong dipole-dipole interactions. But one shortcoming of Rydberg atoms is that because the way in which you induce these large electric dipole moments is by exciting your outermost electron, these electron that's excited will decay back to the ground state at a time scale of about microseconds. So your interactions are, so to speak, only there for a fraction of a microsecond. So these are very short-lived. So that's one kind of challenge in working with Rydberg atoms. And then as a second option, which I hope I'll have enough time to talk about today, if not, I'll talk about tomorrow, is using magnetic atoms. And magnetic atoms are atoms that you can find in your periodic table that happen to have large magnetic dipole moments. So the long-range interaction between a pair of magnetic atoms is magnetic dipole-dipole interaction in comparison to electric dipole-dipole interaction. So the interaction between magnetic atoms, a pair of magnetic atoms, is fairly weak. So these magnetic atoms have a typical magnetic moment on the order of about 10 Bohr magnetons. And for comparison, 1 Bohr magneton in terms of dBi is about 0.01 dBi. And because dipole-dipole interaction scales quadratically with the dipole moment, it means that the typical long-range interaction strength of a pair of magnetic atoms compared to Rydberg atoms would be, I think, at least 10 to the 4 or 5 times weaker. So there is long-range interaction, but they tend to be somewhat weak. The plus side of working with magnetic atoms is that they're long-lived. These are permanent magnetic dipoles that you have in your atoms. So if you prepare your magnetic atoms in a particular hyperfine state, this magnetic moment is there forever. So if you, for instance, imagine having an optical lattice and having your atoms kind of tunnel around in your lattice system, with Rydberg atoms, the lifetime of the interaction is actually much shorter than the characteristic timescale for tunneling. Whereas for magnetic atoms, you can engineer it so that it's meaningful. Okay, so that's magnetic atoms. The third platform, which I like the most because I work with them, is the system of polar molecules. So polar molecules, you can actually make them in the ultra-cold regime. You can assemble them using starting from a pair of atoms. I'll talk about that in future lectures. But the bottom line is that these molecules, because of the asymmetry of the electronic cloud, or the electronic cloud shape of the pairs of atoms that we use to assemble these molecules can have a very large electric dipole moment in their fixed reference frame. So these molecules, when they're together, experience rather strong 1/r³ dipole-dipole interaction with a typical dipole moment size of a few dBi. So if you imagine having two particles at about a micron spacing, which is kind of the typical spacing that we would have, for instance, in a lattice system or in gas systems, the characteristic interaction strength converted to frequency for Rydberg atoms would be on the order of 10 to 100 megahertz. The corresponding interaction for magnetic atoms would be on the order of hertz or subhertz. Whereas for polar molecules, it's somewhere in between on the order of kilohertz to a couple tens or maybe even 100 kilohertz. And these polar molecules also, they're very long-lived. Because the way in which these molecules acquire electric dipole moment has nothing to do with electrons being excited. It's innately there because of the asymmetry of the electronic distribution of your molecule. And nowadays, there are a number of groups working with Rydberg atoms, magnetic atoms, also polar molecules, whereas I'll get to it in a bit, but assembling these molecules at very cold temperatures is actually a very challenging task to do. So the number of experimental groups that actually work with degenerate polar molecules in the full quantum regime is very small. So for fermionic molecules, there's MPQ with sodium-potassium molecules and GILA with their KRB molecules. For bosonic molecules, there are only two groups. One of which is Sebastian Rowe's group at Columbia working with sodium-cesium molecules, Bose-Einstein condensates of dipolar NaCS molecules, and then Dajun Wang's group in Hong Kong working with sodium-rubidium molecules. So the list is rather short. And needless to say, long-range interactions in these systems are super interesting. Actually, they're necessary for implementing quantum computing schemes with these Rydberg teaser arrays. I'm not so sure if you've seen this movie before. It's from Misha Lukin's group's recent Nature paper. So you have these rubidium atoms trapped in programmable teaser arrays, so you can actually move the laser beams around while having these rubidium atoms trapped in the teasers. You can shuffle them around in any way that you want. You can have pairs of them come together to implement entangling two cubic gates and separate them back and see that the entanglement is still there even after they're physically separated. So this is kind of the core working technology, the Rydberg dipolar brocade interaction that enables quantum computing in these systems, but also in the many-body direction in these different platforms. Experimental groups have been really doing astonishing work, especially with magnetic atoms probing magnetic quantum fluids, magnetic droplets, and the issue of supersolidity, which I hope I'll be able to talk a little bit more about in today's slides. Also, these dipolar atoms have been put in an optical lattice to simulate what's known as the extended Hubbard model. So the simplest Hubbard model will only have on-site interaction, but these extended models have nearest neighbor and long-range interaction terms and correlated hopping terms. So that's like the next order of complication in terms of us trying to better understand the Hubbard physics to conquer high temperature superconductivity. But these atoms, magnetic atoms in Marcus Greiner's group at Harvard, have been put in an optical lattice with single site resolution. So these dots that you see here are images, fluorescence images of single magnetic atoms in an optical lattice. So if I were to push that analogy to solid state system, it's like having full resolution of single electrons in your ionic lattice system, modulo phonons. To be honest, we don't have phonons in our systems, but in any case. And also these polar molecules that I talked about also are being put in lattice systems and bulk gases and really probing very interesting many-body dynamics, especially spin exchange dynamics, for instance, because these molecules in Rydberg system naturally, to obviously implement very naturally spin Hamiltonians. Okay, so going back to the question of how these systems are cooled down. So before I get on to how we cool them, to give you a sense of how cold these gases are. So the typical kind of temperature that we're comfortable with and very familiar with is on the order of about 100 Kelvin, right? Roughly room temperature. All right. And from there, the typical gas temperatures of ultra-cold gases that we work with are on the order of 100 nanokelvin. So that's like 10 to the, at least 10 to 10 or 10 to 12 orders of magnitude colder than what we were familiar with. If you go that distance in terms of temperature in the opposite direction, you have supernova explosion happening. So it kind of gives you a sense of how crazy these experiments are. And of course, in air, if the particles are moving at its sound velocity on the order of a few hundred meters per second, these alkali atoms that are cooled down to 100 nanokelvins are moving at about a millimeter per second in these gases. So really slow. So they kind of put things in perspective. And so what happens as we cool these gases down to lower and lower temperatures and what it means for them to become quantum, we have to think about the thermal de Broglie wavelength of these individual particles, which you can think of as a quantum mechanical size or the wave packet size of these atoms. And of course, at high temperatures, these are very particle-like. But as we lower the temperature further and further, the quantum mechanical size of these atoms grow with the inverse of root temperature. And at some point, they become comparable to the interparticle spacing, which at this point, you cannot neglect the quantum interference effects or the quantum effects of these particles. And this is what it means for these gases to be quantum gases. So ultra-cold gases need not be quantum, but typically quantum gases are ultra-cold. So there is a distinction to be made. And at these quantum degenerate temperatures, then it starts to matter whether you're working with bosonic atoms or fermionic atoms. So quantum statistics makes a key role here. So if you have integer spin particles, they'll condense into the lowest eigenstate of your trapping potential and become a Bose-Einstein condensate. But if you work with fermionic atoms, they will fill a Fermi sea that you're familiar with in electronic systems. So now finally getting to the question of how these gases are created. So typically these atoms, or these experiments look something like this. So this is a CAD drawing of an experiment that I worked with in the past. And this is about a 3-meter length dimension. And so this is a steel vacuum system. So it's a steel chamber that we construct. We design and construct in our laboratories. And inside the steel chamber, we make sure we have very, very good vacuum in these steel chambers on the order of 10 to the minus 11 torr. So that's about 10 to the 15 times more dilute than air. So the chances of these cold atoms or molecules colliding with a background gas is extremely low. So it's well isolated from the rest of the world. And in this steel chamber, at one end of it, what we do is for an experiment that works with alkali atoms, we'll literally put a chunk of metal, of alkali metal, in the vacuum chamber. It's really a shiny piece of, let's say, sodium or lithium that's inside the vacuum chamber. And then you heat this corner of the vacuum chamber up to a temperature that's higher than the melting temperature of your metal, which for alkalis, it's typically on the order of about 200 degrees Celsius. So they'll melt inside the vacuum chamber, and as they melt, they'll produce very hot vapor of these atoms, very dense hot vapor of atoms in this corner of the vacuum chamber. Some of which actually have the right momentum to travel through this long vacuum tube all the way to a section that we call the main vacuum chamber. To these atoms that have the momentum to travel through, what we do is we shine in a laser beam from the opposite direction and do what's known as laser cooling. The idea of laser cooling is rather simple. So imagine you have a very heavy bowling ball rolling towards you or flying towards you. And in your pocket, you have a lot of very light ping pong balls. If you throw a couple of ping pong balls, it's not going to change the momentum of your heavy bowling ball in any meaningful way. But if you throw 10 to the 9 of them, at some point, the effect will accumulate and the bowling ball will start to decelerate. Now that, you can think of the heavy bowling ball as an atom and the ping pong ball as photons in your laser beam. So the single momentum of these photons is extremely small. But if you engineer your experiment such that you can cycle 10 to the 9 of them per second, you can very efficiently cool these very fast-moving atoms to temperatures on the order of millikelvin. So that's a whopping, how many orders? 5, 6 orders of magnitude cooling in terms of temperature, simply by shining in a single laser beam with the right frequency. But, yeah.
The photons do not interact. The photons do not interact with root cross excitations of the electrons in the atom.
That's key. They do excite the atoms. But the electron will get excited, but then they'll spontaneously emit. But absorption always happens in this direction with a well-defined K vector, whereas spontaneous emission will happen in any random direction. So the net average of that is that you'll always accumulate a single photon recoil worth of momentum per absorption and spontaneous emission. So that's kind of the essence of laser cooling. Yeah.
To understand this physics better, the light is actually absorbed by the atom and then emit in the opposite direction. So it's
The light is emitted in every direction. It's not stimulated emission, it's spontaneous emission. So absorption and then spontaneous emission to any direction. Spontaneous emission, unless you have a cavity, it'll happen in any direction in the 4 pi.
so the absorption is what reduces the momentum in the
Right, exactly. Okay, so that's the inner working principle of laser cooling. But laser cooling only gets you down to about a temperature regime on the order of a millikelvin. There are kind of clever ways to push this limit further to microkelvins and even lower, but that involves a lot of technology and cleverness. But I did mention that you have to make the distinction between ultra cold and quantum. And these gases are kind of cold-ish, but they're not quantum. So in order to reach the quantum degenerate regime, you really need to get down to, for considering realistic densities of the gases that we work with, you really need to get down to nanokelvin temperatures. And because of the way in which laser cooling works, relies on spontaneous emission and photon recoil, there's a fundamental limit on how cold that you can get, because ultimately you need to spontaneously emit your photon. And that gives you two kind of temperature limits of Doppler limit and the recoil limit. And the Doppler temperature limit occurs because of the randomness of the photon emission event. And the typical Doppler temperature limit for alkali atoms is on the order of around a millikelvin to 100 microkelvin-ish. So kind of using standard laser cooling techniques, you cannot easily get to below than about a millikelvin temperature. So that's still not quantum. So you need another technique or approach. And that approach is this technique known as evaporative cooling. So what we do is, to these laser-cooled atoms, we can capture them in the main vacuum chamber using laser beams and magnetic fields. And what we can do is then we can selectively remove these atoms in our trap, only the hot atoms from the trap, selectively. So we can remove the hot atoms from the trap, let them rethermalize, lower the temperature, remove the hot atoms, let them rethermalize, and keep on doing this iteratively. Then the remaining gas will get colder and colder and colder, right? And this is the same what you do in the morning when you get your cup of hot tea and you blow away the hot water molecules from your cup, so evaporation. And that can get you down to really cold temperatures on the order of 10 nanokelvin.
Yeah, so this might be a stupid question, but like you said, it becomes a quantum gas when the individual wave packets overlap between different particles, right?
Right.
But like, so then if you increase the density of the particles, then they have a higher chance of overlapping even a higher temperature, right? So like, what is the catch then? Like,
so I guess to interpret your question, why are we not able to go to higher densities?
Yeah, exactly.
That's a good question. So if we go to very high densities, there are losses, three-body losses. So the driving mechanism of thermalization in these systems is essentially two-body, but the loss mechanism and the heating mechanism is three-body.
Okay.
So at higher densities, you start to lose. So that kind of puts a limit on how dense we can be in order for us to have a meaningful time to perform experiments. Yeah.
So how do you measure such low temperature?
Oh, that's a very good question. Okay. If I go back to, so we do what's known as time of flight imaging. So we have these gases in a trap, right, in our vacuum chamber. We turn off the trap, we let them fly out for some fixed amount of time that we control, and then we take an image. These images are usually shadows. We shine in resonant light and have a camera behind, so the camera will record the shadow of the atoms because of the absorption. And if we know the time duration that we let the atoms fly out of the trap, that's essentially momentum distribution. From the momentum distribution, you can figure out the temperature. So that's how we do thermometry.
Can I ask that?
Yeah.
So how do you actually trap these atoms? Like from what I understand,
How do we trap them? So yeah, cooling and trapping are not the same thing. That's a good question. And actually, you're running into future slides that I'll be covering. But to give a short answer, so there are a couple of different ways to trap cold atoms in our experiment. One of which is magnetic trapping. So these atoms, because of the single electron in the outer orbit, they have a magnetic moment of 1 Bohr magneton. Depending on the hyperfine state of these atoms, they have a scaled magnetic moment scaled by the G factor of the atoms. You can think of these atoms, depending on the internal state of these atoms, having different magnetic moments. So if you apply a magnetic gradient potential, if you apply a magnetic gradient field onto these atoms, these magnetic moments will align and become trapped. You can engineer a conservative trap using mu.b. Another way is to use dipole trapping. So it turns out if you choose the right wavelength of a laser beam and you tightly focus a laser beam onto the atoms, these laser beams can also trap your atoms. I'll get to that in a bit more slides. So the combination of laser cooling and evaporative cooling in these experiments typically gets you down to the temperatures that we want to be in, on the order of 100 to a couple tens of nanokelvin. And an actual experiment that we constructed in our group looks something like this. So the steel chamber that I showed you as a CAD file is hidden in this zoo of mirrors and optical elements. And all the different colors of the lasers are there to manipulate the external and internal states of the atoms that we work with. In our experiment, sodium and potassium. Now, on a separate laser table, we have a laser system that's producing all the different light frequencies that are used to address these atoms in the experiment. Which gets us to the section of light forces to address the question of how we use these forces to trap and control the motion of atoms. And so there are kind of coarsely speaking, two different modes of operation of how you can use laser beams to implement forces, to give forces onto your atoms. First of which is called the scattering force. And this scattering force is what I just described. You absorb a photon, you spontaneously emit, net average of momentum you get on the atom. You do that many cycles. That's your scattering force. So this scattering force is a dissipative force. It's like a friction in your system. And you can use a scattering force, obviously, to cool your atoms. The same way you can throw a heavy ball into a jar of honey and it'll slow down, right, due to the friction. But also you can use a scattering force in a way that you can trap the atoms. So for trapping, you need for the atom to know that if the atom has moved to the right, you need to tell them to move to the left. If the atom has moved to the left, you need to tell them to move to the right or have more force towards the right. And you can give this directionality using a magnetic field. So using a technique known as magneto-optical trapping, even using scattering forces, you can still trap, not just cool, but trap these atoms in the vacuum chamber. But still, scattering force suffers from this issue of temperature limits, Doppler and recoil limit. So typically, if you're using light forces to generate very cold samples in our experiment, we use a second mode of operation, which is a dipole force, which is just the AC Stark effect of the atoms responding in phase to the oscillating electric field that's generated by the laser beam. And this dipole force is actually a conservative force. It's not a friction force. So there is spontaneous, off-resonance spontaneous emission that happens for dipole force, but that's very low. The rate of off-resonant scattering is very low. So you can think of it as a conservative force that you can use to trap very, very, very cold samples like a condensate in. And this dipole force is a working horse behind experiments, for instance, using optical lattices. Optical lattice potentials are generated using the dipole force, using interference. Okay. Actually, I have a lot to cover, but I think I'm moving too slow. So now,
When you're putting this by evaporation or something, then the momentum gets very small, and then there might be some emissions of resonances, right?
resonances for what?
With the incoming beam, the inner particles.
So, yes. So the interaction between a pair of particles is temperature dependent. The scattering cross-section is temperature dependent. But usually in these gases, we naturally assume that they're almost zero temperature. So we always work in the T equals 0 limit of scattering. And you're right. At finite temperatures, the scattering length of the scattering cross-section can change, especially because you have now different partial waves that you can tunnel through. But at very cold temperatures, at T equals 0, you only have S-wave scattering for bosons or no scattering for spin polarized fermions. So, but to be precise, you do have temperature dependence on that. Okay. So the way in which we describe light forces, you can get a very simple picture using a very classical model known as the Lorentz model. So you can picture your atom, your alkali atom, as your core with positive charge and your outermost electron being connected to your core through a spring. So it's essentially a driven harmonic oscillator, driven damped harmonic oscillator. And then your laser beam is essentially just a coherent wave, electromagnetic radiation with an E field that's oscillating in time, that's propagating through your atom. And because if you think in the center of the atom has an electric dipole moment generated by the electron, right? D dot E. Oh no, minus E dot R. And this dipole moment can couple to the electric field of the laser beam. And this drive then has an in-phase response of the atom, of your harmonic oscillator, and out-of-phase response of your harmonic oscillator, which gives rise to the dipole force and the scattering force. And this part of the theory, it's not even a theory, it's a description I'll kind of skim through. If there's enough interest, I can cover it more in the Friday's session, the problem-solving session. So this, in the interest of time, I'll skip through and just give you the result. And say that if you do a full proper quantum treatment with optical Bloch equations of the light forces, you get two distinct force terms, one of which is a dipole force, and the second which is a scattering force. The dipole force is proportional to the gradient of your Rabi coupling. So, and it also depends on the detuning relative to the transition that you're working with. Okay, so if you have a two-level system, your atom in the ground state, in the S state, and the excited P state, and if your wavelength of the laser that you use to give forces is blue detuned, so more energy, if you work out the sign, these laser beams will actually repel the atoms. If they're red detuned, they'll attract towards the high intensity region of your laser beam. So using this dipole force, you can actually choose your wavelength in a way that you can either repel or attract in the high intensity regions. And the scattering force is just the momentum of your photon h bar k times the scattering rate of your atom. So this is the probability of your atom being in the excited state if you use a full optical Bloch equation to solve it out. So all in all, the maximal scattering force that you can give is just the photon recoil times the maximal scattering rate, which because of saturation, it's not the excited state spontaneous decay rate gamma, but it's gamma divided by 2. That's because of saturation in a two-level system. Okay.
What is omega?
The capital omega, it's a Rabi coupling. So it's essentially the intensity of your laser beam. Yeah. Delta is the detuning relative to the two-level resonance. And gamma is the excited state line width. So if you have an alkali atom in the S state and the P state, that would be the P state line width. Okay. So this is a movie that I found on YouTube from Tom Killian's group at Rice. I think it's strontium atoms being laser cooled. So if you look here, you'll see this blue dot appearing. It'll appear again. Yeah, this one. So these are strontium atoms that are laser cooled using the dissipative force. And what we see is the spontaneously emitted photons reaching our eye. In this case, of strontium atoms. So the strontium transition is blue in the UV. Okay, so I've already covered the working principle of evaporative cooling. And so for efficient evaporative cooling, you already asked the question. So for evaporative cooling to be efficient, we typically require a high number of elastic two-body collisions compared to inelastic three-body collisions on the order of 10 to the 3 enhancement. So if your density goes up, your inelastic loss rate will spike up and then you'll lose. And the way in which we remove atoms from the trap, in a dipole trap, it's simple. You just reduce the laser beam intensity, and that'll naturally force the hot atoms from the trap. In a magnetic trap, because hot atoms feel a stronger magnetic field because they can climb to higher regions of your magnetic field. So locally, their magnetic resonance frequency is different. It's temperature dependent. So you can use that to only shave off the hot atoms from your magnetic trap and just reduce the temperature gradually. So that's how evaporative cooling usually works. And of course, how could I not show this picture in India? And if you work with bosonic atoms, this will give you Bose-Einstein condensation, which was first observed in 1995, first at Gila and then at MIT. And of course, this is the birthplace of the Bose distribution, so I'm very honored to be here. So there.
So if you take cesium atom, then we cool the atoms using optical molasses, then we use more to trap it. Generally, the temperatures are around 40 to 50 microkelvin. You are getting very good.
So that's because polarization gradient subdoppler cooling works.
Yes, subdoppler.
Yeah, so I didn't cover subdoppler cooling, but if you have Sisyphus cooling,
Yes.
then you can go to lower than the Doppler cooling temperature.
But I think it is around microkelvin, 40 to 60, not less than.
Yeah, so using Doppler cooling, you can get down to a couple tens of microkelvin. Using subdoppler cooling, you can get down to a couple tens of microkelvins-ish temperature.
But you are telling here microkelvin, millikelvin.
If you don't do subdoppler cooling, if you just do vanilla laser cooling, Doppler cooling, that'll be on the order of millikelvin, couple millikelvin. Yeah. Yeah. So if you ignore the Sisyphus effect, then that's the temperature limit. But Sisyphus effect allows you to go to colder temperatures, which is why Bill Phillips was so surprised in the old days of laser cooling when he saw that the sodium temperature distribution was so narrow compared to the theory. That was a pleasant surprise. So there are a number of different groups in the world working with cold atoms. There's a website that keeps track of all the groups, experimental groups, online. And also in India, there are 2 groups. I think one here at TIFR. I'm assuming that you're... Right. And another professor at the Raman Institute, I think. Oh, sorry. Excuse me. Okay, so also in Korea, there are 4 experiments in Korea. So in my group, we use these techniques to work with sodium and potassium mixtures. So we can cool sodium atoms, but also different isotopes of potassium, one of which is a fermion, and two of which are bosons. So if you simultaneously cool sodium and potassium-41 atoms, mixtures, into these very cold temperatures, you'll see a dual Bose-Einstein condensate, a Bose-Einstein condensate of sodium that's kind of circling, that's kind of covering the potassium-41 Bose-Einstein condensate. And there's repulsive background interaction between the two atomic species, which is the reason why you see this hole on the sodium condensate that's repelled by the bosonic potassium-1 condensate. And of course, we can also change our laser cooling frequencies and laser cool potassium-40, which is a fermion. And in this case, when we cool the mixture down to very cold temperatures, instead of seeing a condensate, obviously because these are fermions, you see a degenerate Fermi C together with the Bose-Einstein condensate of sodium. So in this sense, we have access to Bose-Bose and Bose-Fermi mixtures. Okay, in the remaining time, I've already gotten a lot of questions about the interaction between these atoms, so I'll try to explain a little bit more about interaction between ground state atoms, not long range, but ground state. So let's consider the interaction between, my battery just died, so it would have been nice if I had a stick, which I do. So if you consider the interaction between a pair of atoms separated by R, of course, because the density is so dilute, we only care or consider two-body interactions. And very rarely would we have to consider three-body interactions. For instance, if we're treating FEMO physics, we would think about three-body interactions, but usually you only consider two-body interactions. So a pair of atoms, atom A and B, separated by R, at first sight looks very structureless, but it's not, because these atoms are actually consisting of ion core and an outermost electron. So for a pair of alkali atoms, we have two atoms separated by R, but the atoms themselves consist of a shielded core and one outermost electron, which can have a dipole moment, electric dipole moment, and a second atom with a dipole moment minus E times the position of the electron RB. Okay. So if you just write down the Hamiltonian for this pair of atom, you have the, let's say we work in the reduced mass frame of the pair of atoms so that we have the relative kinetic energy term, which will give rise to partial waves, which you can treat in a separate way. But for now, we'll just consider the internal structure, so we'll kind of neglect the kinetic energy term for now. Then you have the kinetic energy of the electron, the Coulomb interaction with the ionic core of the atom for particle A, for particle B, and then the pairwise Coulomb interaction between electron here, ion core here, or electron here, and vice versa. So this defines the interaction Hamiltonian. You can actually simplify this interaction Hamiltonian knowing that the distance is much further away than the magnitude of the electron positions, small r. And that'll give you multiple expansion, assuming that the interparticle distance for the pair of atoms is much longer. And simplify such that the electron kinetic energy term and the Coulomb interaction term gives you the atomic Hamiltonian that gives you the electronic states, the fine structure, and the hyperfine structure. The center of mass kinetic energy, center of mass frame kinetic energy gives you the partial wave barrier and the effective Hamiltonian that I discussed. That gives you a P-wave barrier for fermions. But most importantly for this discussion, gives you a dipole-dipole interaction term for the pairs of atoms separated by large distance r. Of course, if these atoms are very close, you cannot do the multiple expansion, and then you have very strong Coulomb repulsion from the electrons coming together and the ion cores coming together. So that gives you the very steep blockade of your molecular potential. Now, since we're assuming large distances, so the interaction Hamiltonian we can treat as a perturbation, we can make use of first order perturbation theory using the eigen basis of the bare Hamiltonian, which is the Hamiltonian of the internal structure of the atoms, so the fine and the hyperfine basis. So if you try to calculate the first order perturbation energy of the dipole-dipole interaction for a pair of atoms in the NL state for atom A and NB and LB state for atom B, the dipole operator, the matrix element of the dipole operator will be 0, right? Because that's a parity odd operator. It's just the position. And these two states are the same. So the dipole operator of your first particle D1, the matrix element of that, is going to be 0 due to parity. Same for particle 2. So to leading order, to first order perturbation theory, the dipole-dipole interaction correction to your energy is just 0. But then that forces us to think about second order. And when we think about the contribution from the nearest p state of the atom as your virtual state and do second order perturbation theory, then you sum over the p state as an intermediate and L2 prime state in your perturbation, which actually has a different opposite parity because L is different by 1 for S and P. So for the second order term, the dipole moment, the matrix element of the dipole moment operator for the between the virtual state and the initial state for atom A and atom B are non-zero. Which is a reason why for these atoms in the ground state, because of the second order effect, you have the van der Waals attraction, where I bundle up all the coefficient in a convenient fashion and call this the C6 coefficient. So for the van der Waals interaction between ground state atoms, it's essentially the dipole moment is fluctuating. The average of the dipole moment in the ground state itself, the matrix element, is 0. But because of the external, because of the virtual state, it's kind of fluctuating. So in that way, the dipole moment of atom B kind of induces a dipole moment on atom A, and that leads you to a van der Waals type of interaction. Okay. And of course, if you put in your atomic structure into work for alkali atoms and you just include the effect of the excited p state, you can actually do a rough calculation of the C6 coefficient. And you can write it this way. And importantly, for these Rydberg excitations, right, for Rydberg atoms, the mechanism in which Rydberg atoms acquire interaction is the same. So the interaction between a pair of excited Rydberg atoms is also a 1 over r to the 6 interaction. In that sense, it's not strictly long range, but I like to say it's long distance. The key difference between a pair of atoms in a quantum gas that's colliding compared to the Rydberg atoms in higher orbital states, high n states, is that for a pair of atoms, the characteristic length scale that arises from the van der Waals interaction is much, much shorter than the typical interparticle spacing. So to simplify our lives, we approximate this as a simple contact interaction. And if you solve off the scattering problem, all the phase shift that you have in the outgoing wave, you just bundle that up into an effective parameter known as the scattering length, and approximate your interparticle interaction for alkali atoms as a delta function. Whereas for Rydberg excitation in your tweezers, for instance, the characteristic van der Waals length for high n states is actually comparable to the spacing between your Rydberg atoms on the order of a micron. So in this case, you cannot treat your interaction as short range, and you actually have to consider the full 1 over R6 dependence, which they do in their Rydberg experiments. So bottom line is that for a pair of atoms, because of these reasons, we approximate the interaction between a pair of ground state, electronically ground state atom as a delta function times the scattering length and the relevant parameters that turn this into interaction. And we conveniently bundle up the constant as and give it a name. We usually call it a G times the delta function of the separation, so contact interaction. And if you have distinguishable particles, this is correct. If you have identical bosons, you have bosonic enhancement. So the actual interaction strength is times 2 of this. So it's 4 pi h bar squared over the reduced mass times scattering times the delta function. If you have spin polarized fermions because of Pauli blocking, this is times 0. So you don't have interaction. So spin polarized fermions in the ground state are non-interacting. You have to have a spin mixture to interact. And the typical scattering lengths of alkali atoms, if you're curious, I've just listed them here. And the key thing that I want to emphasize, which I'll cover in tomorrow's lecture, is that this scattering length, which is a single parameter that characterizes the strength of the interparticle interaction potential, you can actually tune between minus infinity and plus infinity using a technique known as Feshbach resonances. So this is the essential handle that gives strong power to use these atomic gases to quantum simulate interesting many-body Hamiltonians. Okay, so I already covered this. So for typical Ripper-Teaser experiments, the interparticle spacing is on the order of 2 microns, a few microns, and that's comparable to the van der Waals length for high-end states of these atoms.
So, already you mentioned on this slides that if you consider 2 Ripper exhibitions, 2 neighbor Ripper exhibitions,
right?
Then there's a huge penalty. There is a repulsion.
Yeah, that's the Ripper blockade.
Can you repeat that part?
Oh, the Ripper blockade I haven't covered here. I'll cover it on either Thursday or Friday. I think it's better if I do a proper explanation and then.
You already have the C6 coefficients you shown there. And,
Yeah.
I think that the ratio of C6 by something was a few slides.
Here. Yeah, so for Ripper interaction, the dipole-dipole interaction is actually proportional to the principal quantum number times the power 11, which is why it's still a 1 to the r interaction, but it's huge because it gets enhanced by a factor of n to the power 11. And the typical values of the principal quantum number for the Ripper atoms is on the order of 50 to 70. So you get a huge enhancement by increasing the size of your electronic cloud that makes your atom very polarizable.
And also in this centrifugal gradient that you h bars by twice L to L plus 1.
Yeah.
So that I guess that the dependence with the temperature, if you increase the temperature, is through the separations, right? Because the higher L modes are also allowed.
Yeah. So high temperature you can easily tunnel through, or even your collision energy could be higher than the barrier height. And then that'll make a very strong change in the scattering behavior.
The separation.
Huh?
Temperature dependence, where it comes through in this expression, the temperature dependence.
Does the temperature dependence come through this particular expression? Not really. You have to put that in your scattering wave function and the entrance energy. Yeah. But the potential is a potential. Yeah. Okay, so that's all I wanted to talk about in terms of typical alkali atom quantum gas experiments. But I promised you long-range interactions, and today I wanted to talk about one of the ways of getting long-range interaction in these gases is by using what's known as magnetic atoms. So I told you that for alkali atoms, you have a single outermost electron with a magnetic moment mu b, a Bohr magneton. So that's kind of the magnetization that you have of typical alkali atoms. But for the so-called magnetic atoms that are very heavy with outermost electrons or with unpaired inner shell electrons in the d or the f orbitals, these unpaired inner shell electrons collaborate together with the outermost electron to generate huge, well, not huge, but much larger magnetic moments of the atoms. Okay? So typical structure of magnetic atoms that are used in these laser cooling experiments are, like, for instance, chromium, dysprosium, and erbium. And chromium has a single outermost electron in the S1 state, but the inner, it's a D5, so you have 5. You don't have, I guess you have 2? PD. You have 2 unpaired electrons? One unpaired electron. I think you have to be careful about calculating the magnetic moment, but you have unpaired you have unpaired electrons in the inner shell that can collaborate with the outer shell to generate very large magnetic moments for chromium, 6 mu Bohr, dysprosium 10, erbium 7. So that's 6 times, 10 times, 7 times more magnetic than a typical alkali atom in the 1s shell. And because dipole interaction scales quadratically with the moment, the actual strength is square of this gain. So these are kind of moderately strong, moderately dipolar, let's say. These atoms are. And one thing about these magnetic atoms is that these magnetic moments are permanent magnetic moments. These are not induced magnetic moments. So when you apply a magnetic field onto your atoms, there's no kind of, for instance, for polar molecules, the electric dipole moment is an induced electric dipole moment. If you apply an external electric field, the molecule polarize or rotate along the electric field, giving you controllable size of the moment itself. Whereas for the magnetic moments, these are originating from electrons, not because of some orientation of your particle. So when you apply a magnetic field, you have that magnetic moment aligned with respect to your field. You don't have continuous tuning over the size of the moment in these experiments. The kind of tuning that you can have is by choosing the MJ state that you work with in your gas experiments. So given a magnetic field direction that's your quantization axis, you can use RF photons to switch between different MJ quantum numbers of the atoms that you cool in your trap. So that's kind of changing the kind of, if you imagine your magnetic moment persisting around your magnetic field, being in different MJ state just changes the precession angle, which changes the average magnetic moment along the magnetic field direction. So in that sense, you have a discrete way of controlling magnetization in these atomic gas experiments, magnetic gas experiments. It's not continuous, is what I want to emphasize. And of course, then the tuning that you have in terms of the size of the magnetic moment is discrete, but you can change the direction of your magnetic field in relation to the trapping geometry. For instance, you can trap your atoms in a single layer pancake trap, and if you tilt your magnetic field to be in plane, then along that direction, your atoms are attractively interacting, whereas side by side, they're repelling. If you align your magnetic field perpendicular to your plane, these magnetic atoms are repelling with 1/R3 repulsion. Okay, so that's the kind of control that you can have. And I guess these things are kind of the things that I want to present in front of a group of theorists, because I think it's also very important, because eventually theory itself is very beautiful, but it's more beautiful when you're actually successfully describing a real experiment. And there's usually this gap between experimentalists and theorists. And from our side, in terms of understanding what the theorists can do, but from the theory side, understanding what experimentalists can do. And so one of my goals is to try to convey the sense of what we can actually do in the experiments with a reasonable amount of effort. So the kind of control knobs that these magnetic atoms have is a discrete control of the magnetic moment size and the direction, also the tilting angle, together with the geometry of your system is what you have. Okay, so I have 5 minutes left. So using this control of these highly magnetic atoms, a lot of experimental groups have been doing fantastic work in recent years, for instance, observing the Fermi surface deformation in a dipolar Fermi gas. So as I said, if you have a degenerate Fermi gas of your magnetic fermionic dipolar magnetic atoms, you tilt your magnetic field to be in plane. Your Fermi C will contract along the magnetic field direction and bulge out perpendicular. So this is an experiment that observed that for the first time in year 2014. So that was quite some time ago. And more recently, with magnetic Bose-Einstein condensates of these magnetic atoms to observe the physics of quantum ferrofluids, quantum liquids, magnetic quantum liquids, and also rotons in these systems, and evidence for supersolidity in these magnetic gas systems is one of the very highlighted experiments in recent years coming out of magnetic atom community. And as I've already shown you, these magnetic atoms have already been put into a microscope objective to simulate the extended Hubbard model, and so on and so forth. And so in the remaining time, I guess I have about 3 minutes left. I can briefly discuss one of the interesting aspects of these dipolar magnetic atom BECs in the direction of supersolidity. I'll make this quick. So superfluidity, I think everyone is rather familiar with by now, at least in principle. So it's a superfluid, it's a phase coherence is key in these superfluids. Solid, we know what it is. It's a periodic structure. So a super solid, you can think of it as a super solid that has a periodic structure that's innately built into your system. Not because you enforce some lattice, but spontaneously built because of the Hamiltonian of your system. So whether from a perspective of a solid, it would be a solid that can flow without or move without friction. From the perspective of a superfluid, it would be a superfluid that has spontaneous periodicity in your fluid. So either way, whichever direction you feel comfortable. So there's been this suggestion of the existence of the supersolid phase a long time ago in the 70s by Chester and also by Anthony Leggett. And actually, I'm not so sure about the year. I think it was about 20 years ago. At Penn State, there was a very pioneering experiment at the time suggesting the observation of a supersolid phase in liquid helium, in very cold helium systems. And I don't work with helium ever. Surprisingly, I work with cold atoms, but I don't work with helium. But in any case, to the best of my understanding, they look at this torsion mode of helium trapped in this torsion oscillator. And as they cool down, they try to see the change in the torsion frequency and try to understand that and try to suggest the existence of the supersolid phase. But of course, I don't know if you've been following, this result has been refuted by the same research group that in fact it was most likely a different phenomena that they observed instead of supersolidity. So since year 2012, it was still kind of open question whether the supersolid phase can actually exist in nature and in what kind of system it could exist in. And to everyone's surprise and excitement, condensates of magnetic atoms in trapped geometries in 2D or 1D have a very strong hint. I think people now really believe that they have observed the supersolid phase in these condensate experiments. So I'm already out of time, so I'll make things quick. So the typical way of theoretically describing a gas of interacting bosons, you just write down the Hamiltonian, you have your free particle dispersion, k squared, and then you have your pairwise interaction, two-body interaction in momentum space. And the simplest thing that you can do is just a mean field treatment. So you assume that most of your atoms are in the ground state, so you treat your A0 and A dagger. Zero, the 0 is a label for the ground state. You just assume that there's root N0, which is the number of atoms in the ground state in the condensed phase. And you just do mean field and keep the, you throw away the 4 A terms and just keep the pairwise terms to arrive at this Hamiltonian, which includes the kinetic energy of the bosons in the excited momentum states, the self-interaction energy of the bosons in the ground state, so that's the BEC self-interaction energy, and then other interaction terms that describe interaction between an atom in a condensate and an atom in the non-condensed higher K state, and then pairwise creation and annihilation of atoms in BEC to a non-condensed phase and non-condensed state to BEC. So that's just the mean field treatment of this. If you're interested, I can go through this in more detail on a Friday and the problem solving session. And once you write down the mean field Hamiltonian for the bosons, you do the Bogoliubov transformation, which you do also for fermions in the Bogoliubov-Dugen treatment. So you have your alpha and alpha dagger Bogoliubov operators in K minus K dagger with a bosonic commutation relationship, and you have a redundancy in the way you define your operators, so you have kind of a gauge freedom that you use to enforce this relationship for the amplitudes of the operators. And after some substitution and dirty math, you can figure out the dispersion of your Bose-Einstein condensate to be the square root of your free particle dispersion squared times the free particle dispersion times the density times the Fourier transform of the pairwise interaction. Okay. So, it's lunchtime. I shouldn't be pushing too hard. So the bottom line is that you can take the Fourier transform. So for a pair of magnetic atoms, you have the contact interaction, right? Because these are bosons. But on top of that, you have your dipole-dipole interaction. You can take the Fourier transform of that and plug it in to get your dispersion of your dipolar BEC. And in 3D, yes, your dipolar dispersion has an angle dependence, causing deformation of your condensate along the attractive direction, for instance. But it doesn't have, in 3D, it doesn't have any sharp K dependence, if you actually work this out. But if you actually confine these atoms in a lattice into a pancake or in a tube, the confinement direction, when you integrate out the confining direction, it gives you a very sharp K dependence around the tight confining length scale. So here I'm assuming that you have a pancake, a quasi 2D sample of a boson, of magnetic bosons, with the harmonic oscillator length along the tight confining direction LZ. So around the 1 over LZ momentum scale, when you actually calculate it out, you see that the dispersion has a very sharp dip, reminiscent of the Roton spectrum in helium. And the reason for this energy dip in the dispersion, you can kind of conceptually understand it in this way. So if you have low momentum collision, so small k, so very long distance, in a quasi 2D trap, your interaction is mostly repulsive, right? Because your atoms are trapped in a 2D trap, and presumably you've aligned your magnetic moments to be perpendicular to the trapping plane. But at high k, very high k, the collision distance is actually it can be short. It can be shorter than the thickness of your quasi 2D trap, which at that point you open up an attractive branch in your interaction. So that's kind of a hand-wavy way to understand why in these dipolar systems you have this attractive lowering, softening of your dispersion. And this K Roton mode actually gives you a characteristic modulation of your Bose-Einstein condensate. And as you make your dipolar interaction stronger, at some point they become separated liquids with no phase coherence. So your condensate evolves from the weakly interacting regime of a single condensate to presumably a supersolid phase, and then to separated liquids. And the question has been for a long time whether you can directly probe the phase coherence of this phase modulated condensate. And in recent experiments, the Italian group has done this torsion experiment in their quantum gas experiment and looking at sharp oscillation frequencies and matching that with theory to kind of argue that they see agreement with the supersolid phase. And then more recently, they've also observed vortices, quantum vortices in the super solid phase, so which is kind of smoking gun proof that these indeed have phase coherence. So that's kind of what the magnetic atom community has been working on in recent days. So in the interest of time, I'll conclude. So if you increase the dipole-dipole interaction even stronger in 2D, there's a theoretical proposal that these dipoles will crystallize and form a self-aligned crystal. And so a lot of the groups, especially working with bosonic molecules, dipolar molecules, are really trying to probe this physics. Okay, so with that, I'll conclude for today, and then I'll see you on Tuesday.